You want to change? Yes. So in the last session, we heard about the ICICLE overall overview of the services, software. So now we'll go into a little bit more details. It will be presented by Professor Subramoni and Brijesh Nanda. Professor Subramoni is an assistant professor in the computer science department here at the Ohio State University. His current research interests include high-performance interconnects and protocols, parallel computer architecture, network-based computing, all things related to HPC and AI. He has been actively involved in various professional activities, academic journals and conferences. He's doing research on the design and development of the MPI, MLAPS2X, and other software packages, and now heavily involved in the ICICLE. And Brijesh is a software engineer and applied AI researcher, leading software, MLAI, and geospatial data engineering for the ICICLE Research Initiative at OSU, where he manages a team of engineers and researchers spanning undergraduate and master's level. His work centers on bridging cutting-edge research with production systems, building foundational models, and all the different pipeline aspects. Before moving into AI research, he spent nearly 4 years as a software engineer, building large-scale distributed systems at Dassault Systems and Avis Budget Group. He holds a master's degree from the computer science department. So with this, let's give a big hearty welcome to both of them.
In this talk, I'll be presenting, so there are two components. I'll be giving the talk with some pre-recorded demos. Then Brijesh will be showing a live demo of those components working at the various supercomputing systems in the US. So the title is From Edge to Annotations, a live demo of ICICLE's software infrastructure. So as Vipin mentioned, the goal of the ICICLE AI Institute was to design the next generation of intelligent cyber infrastructure for a computing continuum. So what does a continuum mean? You can start from, let's say, edge devices like your phones or Jetson Nanos or Raspberry Pis, all the way to supercomputing systems and everything in between. And these can have heterogeneous resources in terms of GPUs of different caliber, CPUs, XPUs, everything in between. Can we compose them in a modular and a plug-and-play fashion so that stakeholders are able to solve societal grand challenges? So we want to democratize high-performance computing and AI, make the solutions modular and plug-and-play rather than plug-and-pray, scale it out, and see if it can work across the computing continuum. In this particular talk, I'll be focusing on precision agriculture. So what is the state of the art in precision agriculture? You have a few large agtech companies like CNH Industrial, PTx Trimble, John Deere, who come up with solutions for a small number of agricultural use cases and crops like corn, soybean, wheat, or cotton, which is the cash crops in the US. And they only serve a small number of stakeholders, which means that this is not democratized. There is no portability because there is no desire for John Deere to work with a solution from PTx Trimble or CNH Industrial. They won't make money. So why make it portable or plug and play? And finally, it does not serve the computing continuum from edge to the computing cloud. But all farms are unique. So before I began this project 4 years ago, I knew next to nothing about agriculture. Still, I am blissfully ignorant about most things, but I'm learning. What I learned is that all farms are unique. So the solutions for those farms should be unique. So soybean grown in the north of Ohio is vastly different in terms of quality and input, as well as the cultural practices used from soybean grown in the south of Kentucky. Okay, so solutions also need to be unique. Large organizations lack the bandwidth or the financial incentive to tailor such solutions. However, the solutions that these organizations have pitched have shown to be significantly impactful in terms of reducing the use of chemicals. For instance, precision spraying solutions from John Deere has shown a reduction of up to 70% in the use of chemicals. So the grand challenge we are trying to solve here is, can an AI-powered HPC-enabled solution be created to gather and process data, train a model using that data, infer using those trained models for a particular problem which is of societal importance? So the future that we're envisioning is one where a variety of partners are able to use the solutions for a variety of use cases and for a variety of stakeholders. So we really want to democratize this. So why Android? So when iPhones came in late 2000s, they really blew out the competition out of the market. Why? They had a very nice ecosystem of hardware, operating system, and more importantly, apps. I use this phone because of the 100 odd apps that I have on this phone. Okay. Can we do similar for the agricultural space where ICICLE forms the operating system or iOS or Android for the space where a variety of hardware vendors and a variety of application developers. These could be people who generate data, who generate models, who try to infer on those models, who try to distill those models, come around the ICICLE cyber infrastructure. So we hope that this is the pipeline around which this can happen. So this covers everything from data collection, data movement, data pre-processing, to model training, inference, visualization, and finally doing the crop management intervention on the field. Now, there are more than 100 different software components which become part of this pipeline. I'll highlight a few and see and demonstrate how they enable plug and play, scaling from edge to cloud computing, and also cover the computing continuum. So this is a visualization of how the pipeline enables data collection and data transfer from on-field equipment like drones or tractors to a high performance or edge computing system where you would either train or infer on that data, post-process that data for either textual or human readable or machine readable output, and feed it to the appropriate people or hardware on the field. Now, as part of this, I'd like to show 3 different software components that we have developed. So one is the ICICLE Edge Management System, the no-code image lab, and the semantic segmentation and annotation. So all of these mostly come in the first portion of the pipeline where you collect and pre-process data. The edge management service allows you to handle, orchestrate multiple edge computing systems like your Jetson Nano or Raspberry Pi, deploy a particular model there for on-the-field detection or crop management intervention. Once you have collected that data, then you might want to process that data. So you need to make the data AI ready. Sometimes an RGB image may not be easily distinguishable by an AI model. So can you convert the RGB image to the HSV or the LAV spectrum? So that is where the no-code image lab comes into play. It gives you several tools to pre-process this data. And finally, once you have pre-processed your images, can you do annotation pretty quickly? So collecting data is cheap, but good AI depends on good data. So can you label that data in an efficient fashion with little effort from the human there? So that is the third tool. Now I'll go into each one of the tool in a bit more detail and show a short demo. Brijesh will then give a live hands-on demo. So the ICICLE Edge Management Service is a control plane for deploying computer vision models on heterogeneous edge devices. Could be Raspberry Pis, could be Jetsons, could be laptops. So the idea is that you will register those devices, you will push either containers or models onto those devices, and launch them, tear them down, start, stop, all of these from a remote portal. Okay. The following video shows how it all works.
Login. The demonstration begins with a secure login to the IEMS portal. Device registration. Next, a new Edge device is registered with its hardware type, camera setup, and unique name. Agent installation. The portal then creates an installation package. Running it connects the device and starts the Edge agent. App launch. From the device page, an artificial intelligence application can be selected and launched remotely. Live stream showcase. Once deployment is complete, the live camera feed appears with real-time corn residue detections.
So this is an example of
Group launch. The same application can also be launched across an entire device group with one action. Multi-camera view. Finally, the multi-camera dashboard brings several active streams together for centralized monitoring.
So this is the software that we had created to orchestrate the use of multiple edge devices. You could do the same thing and manage 1, 10, 100 different edge devices from one portal in a very easy manner. Okay. So now that you have collected the data, how do you do the initial set of basic CV processing on the data? So this is where the image pre-processing studio or the no-code image lab comes in, which is an OpenCV based pipeline builder to apply a variety of basic computer vision techniques on the input image.
I'm presenting the no-code image lab, which helps visualize and perform pre-processing workflows and allows us to submit jobs for large-scale pre-processing. As you can see, I have uploaded an image from an available cluster. I can apply various pre-processing operations. For example, I'm modifying the HSV channels by adjusting the U and visualizing it. Next, I'm inverting the scale and then sharpening the image. There are several other pre-processing options available, so you can combine different techniques to enhance regions of interest. Finally, we can prepare a job for submission by entering details like the input image directory, the output directories, allocations, the systems or cluster to run in, and submit a job.
So the benefit here is that you look at one image, apply a set of operations on that, then the system that we have created allows you to replicate that same operation or on hundreds or thousands of millions of images on the same data set. So this significantly reduces the amount of human effort required. So once you have done this pre-processing, the next step will be to do higher value operations and preparing the data set for either classification, segmentation, or detection kind of tasks. So this is where the smart labeler comes in. So this uses foundation models to help human experts annotate the input data set for either classification, detection, or segmentation. So the following videos will show some of those use cases, and Brijesh will then show a hands-on demo of them.
I'm presenting the smart labeling service for object detection. As you can see within the dashboard, you can upload your own data to any given cluster. You can create your own pipeline here. We'll enter a demo pipeline for now. You can create annotations using the draw tool, or you can use SAM3 segmentation assisted annotation. We have two options. One is single click, which uses coordinate prompts. The other one is text prompts. This is zero shot annotation. Now we entered few shot annotation where we optimize path size based on intersection over union score in that page. Later, we proceed towards object detection and classification by initially selecting a proposer which generates regions of interest along with a confidence score. Then the embedder is used to perform similarity checks to classify the regions of interest into different labels.
So that was the example for creating a data set for detection purposes. This is the same tool, but for generating segmentation masks.
I'm presenting the intelligent semantic segmentation service, which helps perform zero-shot semantic segmentation. There are two ways to do this, either by manually drawing masks or segments, or by using AI assistants, where you can supply coordinates or text prompts.
So these are the set of tools that we have created. Again, this only comprises of a small set of tools. Now let me hand it over to Brijesh so that he can give you a live demo. In the meantime, if you have any questions, I'm more than happy to take them. Go ahead, Brijesh.
Uh,
Go ahead.
Hello, everyone. I hope I'm audible. So I'll be showing a live demo of the smart labeling tool for object detection that we have. Why exactly do we need this? Nowadays, a lot of data is available. Maybe those are images captured through drones or through any other means. Now, a valuable data set actually not just involves raw images, but also involves labels, bounding boxes, as well as annotation masks around the regions of interest. So that's where this particular pipeline or tool comes into picture, where it'll allow us to create these large data sets, maybe comprising of 10,000 or 100,000 or even million images. Now, in order to start with, so we divided the whole processes into two stages. One is zero shot annotation, the other is a few shot annotation. Now I'll be demoing the zero shot annotation process. So in this particular page, we have a UI interface in which we can perform annotation either through drawing boxes over the objects of interest. For example, here it's a cow, or by using AI-assisted annotation. So if you want to perform AI-assisted annotation, so we go ahead and click that particular option. And we have two different options. One is single click. We provide coordinate prompts to the foundational models to basically detect objects which is in its vicinity. For example, if I enter a given label and if I select this option, I can go ahead and click on objects here. I can just point to the objects here by clicking on them. As you can see on the top right corner, prediction is in progress, and it will automatically draw a box around the region of interest. So similarly, if we feel that think about the amount of time we saved, we dragging and dropping boxes, labeling, when compared to this, just pointing towards the points or regions of interest. If you want to still reduce the time of annotation, we can go for text prompts based annotation. So here we enter all the objects of interest. For example, there are shadows as well here, cows, shadows, etc. And we have SAHI as well, which stands for slicing aided hyperinference. So instead of performing inference on the whole image, we split it into multiple overlapping sections or tiles, and we supply them for inference. So what it does is, instead of supplying a 5000 by 5000 image onto a model which consumes probably 960 by 960 image, we cut it down. Because when we compress 5000 by 5000 to probably 960 by 960, we are basically downsampling a large image down by a scale of 5. We are losing a lot of details, and especially in images like this captured through drones, finer details also matter a lot. So I'm going to we can enable or disable that. Then we have options to enter the confidence thresholds that we want, as well as the mask precisions that we are looking for. Then we can click on enter. As you can see, prediction is in progress. It will automatically draw boxes around all the regions that we are looking for. Yeah, so these are the results for it. So similarly, we can use this particular tool to draw annotations over any objects of interest. So apart from that, we can filter out annotations based on confidence scores as well. And we can eliminate annotations based on the scores. And we have non-maximum suppression operations as well. For example, multiple prompts have been performed on the same image. Because of which there are multiple overlapping boxes. Now, how do we eliminate those overlapping boxes? So we can use non-maximum suppression over here, along with the intersection over union scores. So anything overlapping above this particular intersection over union scores will be eliminated from the image. Then we have a review mechanism as well. We have filtration mechanisms as well, and we can import annotations from the work of any previous annotator, researcher, etc. So this is the zero shot annotation method. So from this we can progress onto few shot annotation. So now, for how many images can we do this? So as a researcher, we usually don't have that much time to annotate probably 10,000 or 100,000 images. So because of which we need to go into a few shot annotation mechanism where to the process or to the pipeline, we provide a few examples. For example, here we annotated, let us say 10 images with 10 or 20 samples each. So we provide these samples to rest of the process saying, okay, this is cow, this is sheep, or this is any other rare species that we are looking for. Go ahead and find all the other objects similar to this. So that's where rest of the pipeline comes into picture. And here we divide the whole process into two different sections. We combine the capabilities of multiple models. So these so one section involves processor proposers. The other section involves embedders. So proposers generate regions of interest. It doesn't classify the objects. It'll just generate regions of interest. And the embedders will generate feature embeddings, vectors, or numerical representations of those proposers, so that we can use these vectors to compare it with the ground truth that we provided to basically classify. So we have basically used multiple models like SAM3, OWL-V2, Dino, BioClip, etc. We have combined the capabilities of all to enable this particular result. And even when we use OWL-V2, example for the generation of, let me just select a file. When we use, so we basically, this is an example where we have used OWL-V2 for vector embedding generation. So even during that process, we give a given crop size. As I told you, we use Sahi here. So we give a given crop size, and we tell the model to detect objects which are closer to the objects that we have provided. And we do a comparison of the objects that we have provided and the objects that the model has generated. As you can see, for different path sizes, the results are a bit different. So you can see different results here. So based on these results, so this is a visual way of identifying it. We also have a graphical way of identifying the same. So based on this particular graph, it basically plots the intersection over union scores across all the boxes that we have. So based on this, we select the optimum path size. For example, here the green line, which is for 314 by 314 pixel, that looks best. So we can go ahead and select this as the optimal path size for us for further processing. So similarly, using the proposer, we generate the regions of interest as shown in this particular box. And it comes along with the scores that it has assigned. So these are the scores that it has assigned, and the proposers have just generated the regions of interest here. If we go to the next stage, it will, I won't bore you guys with the configuration, but in the next phase, it will actually classify the final proposals that it generated. So here we have proposals along with the labels for it. So as you can see, there are proposals along with the labels. So this is our whole tool. So initially where we generated a few ground truths, provided those as samples. Then we went to a few shot mechanism where we used those particular samples to perform a similarity check for rest of the proposals that we generated again through multiple proposers. Then we ended up with these annotations. So this is about a smart labeler, and this is object detection. We have a similar tool for semantic segmentation as well. I can just give a quick glance of the tool. Yeah, so the rest of for now, the semantic segmentation pipeline has zero shot annotation included, but we are already in process of including the rest of the few shot annotation process onto the semantic segmentation phase as well. So as you can see now, we get pixel perfect boundaries over our objects of interest. So yeah, this is our segmentation tool, and before we presented our object detection tool. Sure. I can demo the no-code image lab as well. So I'll give a specific example where this is one of the requirements that we got from agricultural engineering department. where we had to find soya beans within the image. So in order to do that, once you see the image, we'll identify the kind of, the kind of difficulty that we face while detecting those. Yeah, so this is the image, and we'll have to calculate the total number of soybean pods that there are within this particular image. So probably for yield estimation, etc. So now, in order to isolate the regions of interest, these pods, we might have to perform several pre-processing operations over it. Now, in order to do that, we can experiment out with all of these classic computer vision techniques that we have here. So in order to begin with, I've already tried multiple of these operations. So to begin with, I'm gonna add in HSV. I'm gonna modify HSV channel. So if I modify HSV channel, so these are the kind of verification that you can or modification that you can see. Then I'm gonna invert the scale. So now we can see the pods are a bit enhanced. Now if I zoom in, you can identify that these particular pods are not exactly sharp enough. So probably it might give a problem when we are doing actual training or inference. So I'll use sharpening techniques, basically apply a high pass filter over it to enable a sharp boundary for the same. And now we have a list of operations here. And now these list of operations are downloadable as operations.json. We have a Python library as well. So we can within the Python library, all we can do is we can provide the source directory. We can provide the location for operations.json that we have downloaded from here. Just provide for submission. Just apply Python 3 point whatever file that you have. So all these operations will be performed on the entire directory that you have. Now, instead of that, we can submit jobs on any of the HPC clusters as well. As you can see here, we have support to OAC as well as expanse clusters. So select the relevant clusters that you have, the clusters that you're interested in, provide the input directory path, the output directory path, then provide the allocation account that you have, then submit a job. It will automatically take take all the images, and it will do all the processing for the entire rest of the image directory that you have. Any questions?
So all of these tools are available for use. So if you would like to use any of these tools, please let us know. They have been deployed on a variety of supercomputing systems, including the Ohio supercomputing system, San Diego supercomputing system, as well as the Texas Advanced Computing System. They are also available on like Amazon and Azure clouds, as well as the National Resource Platform, NRP. Sorry, Noah?
Yeah, no worries. Broadly, with the smart labeling service, I guess I'm interested, what is the primary use of something like that in an agricultural context? Because presumably farmers know having something like that, right?
Right. So the question is this. Farmers can walk their field and count the number of cows or do that. If you have 10 cows, yeah, sure. If you have 10,000 cows, that becomes a challenge. So you need automation. So you need to teach an AI system to do what a farmer has been doing day in and day out for half his lifetime. Okay. Good AI needs good data. So this is going to tell an AI model that, hey, this is a cow. This is how the cow looks like. This is the shape of the cow, so on and so forth. Depending on what that model is supposed to do, if it is just classification, I only need to figure out that this image has something with the shape of a cow. But if the, let's say, target is something like precision spot spraying, I want to figure out the exact GPS coordinates where I want to spray a pesticide. So for that, I'll need segmentation. I just should not say that, hey, this has it. That is one level of accuracy. To go to the next level of accuracy, I should be able to say, hey, this particular exact GPS lat long coordinate is where you should spray, not this 10 feet by 10 feet area. I want you to spray this like 1 feet by 1 feet area. So that is why we want to do this. Yes, a farmer can do this, but what is needed to teach an AI system? So this develops that good data to teach that AI system. Sorry, go ahead.
Also, Sorry, the cow data set, that was just an example. So similarly, in the demo pipeline, we have other kinds of data set as well. So this is one of the data sets where we are detecting oranges. So it's applicable. We are trying to make it as domain agnostic as possible, so that it's applicable to as many data sets as possible. So, and this is just one of the examples. These are oranges. I can show other examples as well in the animal ecology space. So these are drone images captured for zebras as well as giraffes. So it works very well for these kinds of data sets as well. So it's as domain agnostic as possible. Yeah.
Yes, no, that makes sense. Thank both of you.
As I mentioned, all of these tools are available. Yeah, they are free to use. So please do reach out to us if you would like to try out anything. Yes.
I'm trying to put my so I'm very new to iCICLE. I'm trying to put my shoes on for my like retired farmer uncle, and I'm trying to think like what is the how if I'm like a Ohio farmer, how does this get into my hands, or how or maybe it's not even in my hands. It's like somebody like I'm just imagining if I showed this to my uncle, he'd be like, I don't know what confounded technology stuff you're doing here. So I'm like how does that gap get bridged?
Sure. So how do we reach out to the stakeholder? That's a very good question. And that is one of the things that we are trying to do as well. So we are working with various partners like farmers. You have, let's say, always these a few farmers who are extremely risk averse, so or somebody who would be willing to take risks, so we work with them. So we working with the top farmers in Ohio. So there was a presentation we did to them showing how they can generate their own AI models in a very easy to use fashion. So these are small components in a larger workflow. The goal is to see, so I showed you a pipeline earlier, like a flow chart. Can you convert that into a low code, no code workflow where I say, hey, I have this Helio drone, okay, or this image repository, where I captured 1,000 images of tomatoes on my field. I want to train a new model to recognize good versus bad tomatoes, okay? So can I work with a farm service provider? Can I work with a local farmers cooperative? Or can I work with a larger company so that they are able to bring their data? So we are working with, for instance, Kubota. So Kubota has a lot of data for specialized crops like blueberry, strawberry, those kind of things. They want to use our solution to deploy newer models onto their platform. So that is one way in which farmers can get their hands on newer models. Another way would be for us to work with farm service providers. For instance, Apple Farm Services. There are lots of service providers who do broad spectrum application of fungicide, pesticide, weedicide using drones. So currently now it's broadcast application. So we could work with them, and that is one way in which a farmer can use. They could contract it out, and which is what happens mostly with farmers who are managing like 500 plus acres in Ohio. They call in drone operators who would spend a day broadcast applying all sorts of chemicals on their field. They could contract one of these people who would do more precision application. So instead of applying all over the field, they could apply in certain areas. So these are some ways in which farmers could take advantage. But please connect your uncle with me. I'll be more than happy to work with them. Thanks. So if there are no other questions, then I think we are almost out of time. Thank you. Yeah.
So let's speak next to both Hari and Brijesh. So then finally we'll go into a set of short talks. We heard